Hello, and welcome to Physics with Daniel. I'm your host, Daniel Toms. Today we will be focusing on kinetic energy and how to solve for it. We're going to go over the definition, the formula, why it's important, and finally an example. A simple but clear definition of kinetic energy is the energy an object has because of its motion. This differs from the other type of energy, which is called potential energy. Potential energy is the latent energy of an object at rest. So obviously, the biggest difference between the two is that kinetic energy is calculated when an object is in motion, while potential energy is not. Kinetic energy is considered to be a scalar quantity, which means it doesn't have a direction. Kinetic energy is simply described only by its magnitude, unlike other calculations such as velocity, acceleration, momentum, or force. For an object to accelerate, force must be applied. For the force to be applied, work is required. When work is done, energy is transferred to an object, which will make said object move with a constant speed. This sequence of events is known to be kinetic energy. Now that we know the science behind kinetic energy, let's move on to the equation that is used to calculate it. The equation is Ke equals 1/2 the mass times velocity squared. Since this equation is multiplication, the 1/2 doesn't just have to be for the mass. It can also be applied to the velocity squared, or it can be multiplied after the mass is multiplied by the velocity squared. It is also important to note that the equation for the work is equal to the change in kinetic energy. In case anybody forgot, I'm going to briefly go over what we should have found in our lab report. The goal of the lab report was to prove that the change in kinetic energy was equal to the equation of work. To do this, we had to prove that the change in kinetic energy of an object, which is the end kinetic energy minus the beginning kinetic energy, and if the object was at rest, this is 0, is equal to the work calculation that can be seen as work equals force times displacement. You may ask yourself, why is kinetic energy important? Well, it is one of the ways in which we relate mass, motion, and force to describe the state of an object and predict its interaction with the rest of the world. This means that kinetic energy can be seen everywhere, every day. Kinetic energy can be seen if you hit a baseball with a baseball bat, kick a soccer ball with your foot, or even dribble a basketball with your hands. Similar to how it applies to many real-life applications, kinetic energy is used in many aspects of physics. For example, kinetic energy is incorporated into creating safety features for cars. Kinetic energy can be used to find what safety features could protect someone in the event of a car collision. Here is an example of kinetic energy and how to calculate it. Here we see that there is a rubber band that has been fashioned to the chair in the form of a slingshot. We also see a ball that has been weighed to be approximately 0.11959 kilograms. There is a tape measure and a stopwatch that have been placed to the side that will help us find the velocity, which is the last part of the equation that we need to find the kinetic energy of the ball. As the ball is launched, the timer is started to get an accurate reading on the time it takes to reach each measurement. The distance we are going to use to find the calculation is the 2-foot mark, or 48 inches. We can see that the ball took about 0.5 seconds to reach the 2-foot line. Now, to be able to calculate the kinetic energy, we need to do the correct conversions. The velocity has to be measured in meters per second, but we have inches and feet per second. Luckily, the internet has many resources that we can use to find the conversion from inches per second to meters per second. The internet says that 48 inches per second equates to 1.2192 meters per second. Now that we have all the values for the variables in the kinetic energy equation, we can plug them in. Ke equals 1/2 times 0.11959 times 1.2192 squared. This equates to 0.0888 joules. This sums up the example of how to calculate for an object. To sum up what I went over in this recording, we learned what kinetic energy was and how it differs from potential energy. We learned the formulas for kinetic energy and the science behind it. Then we learned why kinetic energy is important in real-life application and in the study of physics. Finally, we went over an example which included a video and a calculation with conversions. That's all, folks.